Hi, Elysia.
Hi,
How are you?
I'm doing good. I uploaded um PDFs. I uploaded PDFs of the lecture notes.
PDFs. Let's go. No more images.
Yeah, I know. Not bad.
No, it's okay. It's okay. It's just joking. Let me get my hotspot and and now my iPad died.
Okay.
Let's see here. Hmm. Over here. Okay, okay. Can you guys hear me? Hello, hello.
Yeah.
Yes. Okay. Um. Okay. Let me go see your Google Drive folder and see what PDFs you posted, and then I'll share my screen.
Okay. Yeah, I wasn't really able to uh title them.
Mhm.
So whatever, I just kind of numbered them by how she numbered the notes.
Right.
So whatever you see is like the larger numbers, like what we kind of just went over on Monday.
Yeah. Let's see here. Um,
Recording in progress.
Share screen. Okay. Okay. So, did you post them under discussion slides or lecture note? Not lecture notes, huh? Lecture notes. Um, Lecture notes 18, 19,
Yeah.
20, 21, 22. Oh, shoot, you posted a lot. 23, 24. Right. Okay, so let's see. Was there a specific notes that you wanted to go over, like lecture notes?
Um, I'm kind of just very new to all these topics.
Yeah.
I wasn't really able to go fully in depth after like Zaitsev and Hoffman.
Mm.
I think like what we were working on is like where I'm left off.
Mm-hmm. Oh, right, right, like the alcohol stuff.
Yeah.
Right,
I
right.
think like Wei has introduced a lot, so
It's a lot.
it is getting a little overwhelming because she introduces like I guess now three different mechanisms per class.
Yeah, the end of 118A and the end of 118B are always very hectic. Like there's a lot of information that shows up. Let's see, second alcohols, tertiary alcohols, 360. So this is the oxidation one. I think it is 21 right here. Yes, this one. Oh yeah, reducing agents. So let me send this to the notability. Okay. Let's see, create new note, done. And this one as well. Okay. Yeah. Okay. So yeah. So for now, we'll focus on this PDF right here because this will cover a good amount of stuff. Um, Without overwhelming you. So you know how in our last thing we went over was oxidation of alcohols
Yes.
with a weak oxidizing agent PCC and strong oxidizing agent Jones. If let's say we hear this is talking about reducing agents, which is the opposite of oxidation. right? Reduction is the opposite of oxidation. Yeah, reduce aldehydes to primary alcohol. Some examples: acid workup. Yes, reaction. Oil of H is deuterium. LiDH4 mechanism. It's more reactive, more selective. Product solvent. Product solvent. Okay, so to review what we went over, primary alcohol would be like if we have an alcohol that its carbon is attached to one other carbon, and if we oxidized it using a weak oxidizing agent like PCC or a strong oxidizing agent like Jones, do you remember what kind of products we would get here? Like, let's look at the first one when we react this primary alcohol with PCC.
If we were to get PCC with that, we would have a double bond to oxygen.
Yep,
And
double bond to the oxygen, right?
and then the hydrogen there.
Right, and the hydrogen here, right, which creates our aldehyde. And you could draw it like that, how I drew it here, or you could draw it out like this. It's the same thing. It's just rotated.
Mm-hmm.
Right. What about if we used a stronger oxidizing agent, Jones? What would we get there?
Is that a carboxylic acid? I know it's an OH and then a carbonyl group.
Yep, carboxylic acid, right? OH and a carbonyl group. That's right. You got it. Because when we use a strong oxidizing agent, we're gonna oxidize that primary alcohol all the way to the carboxylic acid.
Mm-hmm.
If we use a weak oxidizing agent, we're only gonna stop at the aldehyde, which is less oxidized than the carboxylic acid. Right. But if we had a secondary alcohol like this right here, oh wait, no, that's a ketone. Like I gave the answer. It doesn't matter if you use PCC or Jones. Well, that would give you the same thing.
Right.
Which would be what functional group?
Is it an ether?
It's gonna
Or
be
ester. Sorry.
ketone.
Oh, ketone.
Ketone,
Okay.
right? We're gonna add a carbonyl to where the alcohol was right here, right? A carbonyl right there. And because we have a carbonyl that is in between two R groups, this is a ketone.
Okay.
Carbonyl next to an R group and a hydrogen is an aldehyde. Right. Now, if we use a tertiary alcohol, and we try to oxidize it using PCC or Jones, this would be no reaction. And can you think of a reason why this would be no reaction?
Yeah, because it has no hydrogens to give.
Yeah, no hydrogens to give in exchange for a bond to oxygen. Right. So this is the summary of oxidation of alcohols. We could go backwards here from the carbonyl form that we oxidize to go back to the alcohol using reducing agents. So all these arrows here, like PCC or Jones, those are oxidizing agents, right? Which oxidize the alcohol to the carbonyls. But if we want to go backwards, let's say our reactant was like some kind of carbonyl, and we want to go backwards to the alcohol, we have to use reducing agents. And there's two that you're going to be introduced to at the beginning, which is going to be sodium borohydride, NaBH4, and lithium aluminum hydride, LiAlH4. Right. And these reducing agents, they tend to go in two steps, right? The first step is the reducing agent. The second step tends to be an acid workup step. Right. Where if you use a sodium borohydride, NaBH4, we consider that a weak reducing agent. If you use LiAlH4, we consider that a strong oxidizing agent. Right. So if I drew out the structure of NaBH4 and LiAlH4 for you, sodium, whenever you see sodium, always associate that with a positive charge, meaning that the atom attached to it, boron, is going to be negatively charged. So the boron here is negatively charged with 4 bonds to hydrogen like this. Right? And boron here is one of those weird atoms that will get a negative charge if it has 4 bonds. Like we're used to seeing like every atom having 4 bonds and becoming neutral, but boron is one of those 3 weird atoms in the third column that will get a negative charge with 4 bonds. Right? And because this boron here has a negative charge, all of these hydrogens here are going to be nucleophilic. Right? So whenever you think of reducing agents, I want you to think of a hydride ion, a hydrogen with a negative charge, right? Which is going to be the nucleophile. So that's NaBH4. For LiLH4, whenever you see lithium, that's in the same column as sodium. So that's also going to have a positive charge. Always associate lithium, sodium, or potassium with a positive charge, making whatever is attached to it a negative charge. So aluminum here is going to be negatively charged with 4 bonds to hydrogen like this. Right? But these hydrogens here are nucleophilic. They have negative charges because they want to leave. They want to leave with that bond to make this aluminum or boron neutral, right? So let me just give you an example with primary alcohol. I mean, an aldehyde. Let's say we have this aldehyde right here, and in this case, it doesn't really matter what we use. Sodium borohydride or lithium aluminum hydride both would work on an aldehyde, right? NaBH4 or lithium aluminum hydride. You might see some aprotic solvent, like let's say ether, diethyl ether. And then the second step, acid workup. So if I draw out the mechanism for you, here we want to reduce this carbonyl down. So do you remember what it means for a molecule to be reduced versus oxidized? Like what kind of bonds they gain or lose?
Isn't it gain of hydrogens?
Yes, reduction is the gain of hydrogens and the loss of oxygens. That's right. That's reduction. Gain of bonds to hydrogen or loss of bonds to oxygen, right?
Mhm.
So we want to reduce this molecule here. So the way that it's going to gain a bond to hydrogen is that we're going to introduce the reducing agent, NaBH4 or LiLH4. One of the hydrogens here is going to attack that carbonyl carbon right there, right? This carbonyl carbon here is partial positive because it is attached to this electronegative oxygen atom. And because this carbon here is partial positive, that's our electrophile. This hydrogen here is negatively charged because it really wants to leave this negative charged boron to make it neutral. So it's gonna use that bond to attack that carbon right there. But that's gonna break the octet rule, right? Because this hydrogen is trying to make a new bond with that dot carbon. But when it does that, which it will, that's gonna create 1, 2, 3, 4, 5 bonds. So to conserve the octet rule without breaking it, right? We have to pop this double bond onto the oxygen right there, right? That bond right there has 2 electrons. So we're moving these 2 electrons onto that oxygen right there. And do you remember how many lone pairs of electrons this neutral oxygen has right now?
Is it 2 pairs of lone pairs?
Yep, 2 lone pairs, right? 1, 2. So when we do this reaction here, we're gonna give that oxygen a 3rd pair of electrons. Where this is gonna become a single bond O minus now. So when we do this reduction reaction, the dot carbon is still the same, but now instead of a double bond O, we have a single bond O with 3 pairs of electrons. And this is the new bond between, let's highlight this hydrogen yellow, this yellow hydrogen right there. This is the new bond we formed between that yellow hydrogen and that red carbon right there. Right. And what charge would this oxygen have with 3 pairs of electrons and 1 single bond?
A positive?
Yeah, so when we calculate formal charge, right?
Oh yeah, sorry, negative.
Negative charge, right? Because
Yeah,
oxygen is on the 6th column.
It has too many.
Yeah, it has 1, 2, 3, 4, 5, 6, 7 electrons to itself. 6 minus 7, -1 charge, right? But in Gen Chem, you learned a different equation with the divide by 2. It was like something about like non-bonding electrons plus the number of bonds divided by 2. That's one way you can do it, but the way that I think about it is that this oxygen has 1, 2, 3, 4, 5, 6. And we know that this bond here has 2 electrons, but one of the electrons belongs to the oxygen and the other electron belongs to the carbon. Like,
Yeah, so it's one over than what it prefers.
right. So that is a negative charge right there on that oxygen. Right. Now, once we have that, that's the end of the first step. We bring in the second step now, which is the acid workup, H3O plus or H2SO4 or HCl, any acid, to neutralize this O minus. Right, this O minus here is going to grab one of the hydrogens of the acid and just kick out the conjugate base. In this case, it's water, to give us this final product here. And I want to draw it out like this. And you could put water as well, right? Where these two hydrogens right here, I just made them invisible, and they are now going up right there, like that. Right. Oops.
Okay. And I know this is probably like not here yet, but Wei also talked about reversible reactions.
Reversible reactions?
Yeah, so do any of these require that or no?
Yeah, so this first step right here is an irreversible reaction. When we have the hydride ion attack the carbonyl and pop the double bond onto the oxygen to get this intermediate right here, that is irreversible. We draw the irreversible arrow right there. The reason why it's irreversible is because we cannot go back down to form the carbonyl, like reform the carbonyl we had to kick out that hydrogen, right? This hydrogen here and any R group is the worst leaving group you could have in ochem. The worst leaving group ever. Right? It does not want to leave because when it leaves, let's just imagine it leaves, it's going to leave with that negative charge. This negative charge here is extremely unstable. Extremely unstable because it's on a very tiny small atom hydrogen that is not very electronegative. It can't handle that negative charge very well. Right?
Okay.
So that's why it won't be able to go backwards. But in 118C, you'll learn that instead of hydrogen, you might have a better leaving group like OR, chlorine, acetate, which will be reversible because you can't kick those groups out. But in this case, if we just have hydrogen, and any R group, those are the worst leaving groups we have. We can't go backwards. We can't kick those groups out. Right. But the second step here would be reversible. We can go backwards. Right. Because the second reaction here, what we did was we protonated this O minus here. This oxygen grabbed the hydrogen, kicking out the water to give us this molecule here, which is neutral. Right. It could go backwards because some kind of base, like we could use water, like even though it's a weak base, it could still grab that hydrogen. The bond between the oxygen and hydrogen right there represents 2 electrons. Those 2 electrons can go into the oxygen to go back to what we started with here.
Okay.
Right. So in acidic conditions, a lot of the reactions will be reversible. Right. So keep that in mind because that's gonna like show up again in 118B and 118C. In acidic conditions, the reactions tend to be reversible. In basic conditions, the reactions tend to be irreversible. Right. But not all reactions.
Okay.
So that's what reversible means. Like it could go forward and backward, and irreversible is that it can't go backwards. It can only go forward. Right.
Okay.
Right. So our final answer here is that when we reduce this aldehyde, we get the primary alcohol there. Now, I'm gonna give you some kind of ketone, and I'm gonna put the reducing agents NaBH4 or LiLH4, does not matter, because those 2 reducing agents would work with ketone. And second step, acid workup. I want you to walk me through what the mechanism arrows would look like and how you would predict the product. So let's first think about the mechanism first. Right, and then you could look back here for reference if you need, but it's gonna be the exact same mechanism. But I want you to walk me through and explain to me each arrow step by step, each step by step.
Okay. Just for clarification, so when
Yeah.
we have like the numbering, that just tells us like which solvent we're using or like which nucleophile we're using first.
Mm-hmm.
Okay.
Yeah, this solvent here is just, but like, are you talking about this structure here,
Or
or
like when we're numbering them,
numbering them 1 and 2?
yeah, does that tell us the order in
Mhm.
which we're using those? Or
Right. Yeah. So if you see numbers like this, like 1, 2, 3, 4, 5, 6, they're separated by reaction. So just look at 1 first and ignore any other number
yeah.
and see how that would react with the reactant molecule they give you.
Okay.
And then after they react to get some kind of product, you use that product as an intermediate to react with the next reaction.
Right.
Right.
Okay, so I'm just gonna pick Na,
Uh-huh.
well, Na is plus, so we use BH4, and so one of the bonds from that is attached, like the hydrogen, it's going to I think I know it's a small base. I think so.
Mhm.
I think it can go from one of the sides of like the left or right
Mhm.
bonds, and then the arrow is going to draw to the double bond and like give it a negative
Mhm.
charge.
Oh, give what atom a negative charge?
The
Yep,
oxygen.
the oxygen, right. But the hydrogen here, when it attacks that carbon, um, we're trying to break the octet rule here because we're trying to make that new bond. So to conserve
Yeah.
the octet
So like
rule,
yeah, I was trying to say the one aside from it.
oh, this one here, the bond, it goes onto the oxygen like that to give it a negative charge.
Well, yeah, I guess so. I was trying to draw like multiple arrows so I wouldn't break the octet.
Uh-huh. Oh, like were you trying to make this double bond go onto the oxygen first to draw the resonance structure, like this, and this carbon will have the positive charge, and the hydrogen would attack that carbon right there.
Yeah.
Yeah, so that would work as well, but we don't usually draw out the resonance structure to save time, but that does work as well. Like if you just draw out the resonance structure of this, we know that that O minus is there, the positive charge is here, resonance structures of each other, where the hydrogen could attack that carbon instead without any other arrow.
Could we do it where it's the next carbon over? So it's like not the one where there's four already, but do it to the one next of it, so then we can draw the arrow.
Oh, these carbons here.
Um, yeah.
This one right here. So we cannot attack that carbon because let's say that I have that same resonance structure right here with the negative charge oxygen and the positive charge carbon. Let's say that we try to attack this carbon right here on the left that I just dotted out in green. If
Yeah.
I try to do that, I try to make a new bond between the hydrogen and this carbon right here, which is going to break the octet rule. But there's no group that we can kick up, right? We can't kick out the H because that's a bad leaving group, And then these are sp3 hybridized carbons, so they can't do resonance. We can't pop anything up here. So we can't break the octet rule for this carbon.
Oh, okay.
Uh-huh. So we have to attack the partial positive carbon to make a new bond there, which is going to break the octet rule. But to conserve the octet rule, we are able to push this double bond onto the oxygen if we do the mechanism directly, or you can see it through resonance here. This carbon here is missing a bond, right? Missing two electrons because it has a full positive charge. So that means that it's an electrophile. It can accept the two more electrons from this bond right here and the hydrogen, right?
Okay.
Mhm. Okay.
So we're gonna have that bond from hydrogen onto like directly of the double bond, like where the double bond is at.
Yeah, so the hydrogen here is going to attack the carbon of the carbonyl, the carbon double bond oxygen, right?
Okay.
It's going to attack that carbon right there. is attacking this carbon here, the
Okay.
carbonyl carbon.
Right.
Right. So now, if I highlighted this hydrogen here that attacked that carbon, that would be this hydrogen right here. That is the end of the first step. Let's now bring in our second step, H2O plus. What would this H2O plus do to this O minus?
Well, the minus is going to be attracted to the partially positive hydrogen.
Yep.
And then that bond from hydrogen from the H3O plus is going to go to oxygen.
Yes, you got it. Those are the arrows where we protonate this O minus and we deprotonate that H3O plus, acid-base reaction, which is going to neutralize the O minus to become neutral OH, and you have water as well. So whenever you reduce a ketone, you get a secondary alcohol. Whenever you reduce, yeah, it's always the case. Whenever you reduce a ketone, you will always get a secondary alcohol. Whenever you reduce an aldehyde, you will always get a primary alcohol. Right. And those were the mechanisms of how we did that right there.
Okay, so just to repeat what you just said, when you reduce a ketone, you always get a secondary alcohol. And then when you reduce a, we said a ketone?
Yeah, aldehyde.
Yeah, an aldehyde will get a primary alcohol?
Yes, that's correct.
Okay.
That's correct. Yes.
Okay.
So now we talked about aldehyde, ketone, which are two of the oxidizing products we had. We had aldehyde here, or not ketone here, but now we have to talk about carboxylic acid. Whenever we try to reduce a carboxylic acid, right, NaBH4, the weak reducing agent, is not strong enough to reduce that carboxylic acid. We have to use a strong oxidizing agent, lithium aluminum hydride, LiAlH4, to reduce the carboxylic acid. Because the carboxylic acid is a very weak electrophile. So we have to use a strong reducing agent, lithium aluminum hydride, to reduce that. NaBH4 would not reduce that carboxylic acid, which is going to reduce it all the way down to a primary alcohol. So if this is your carbonyl carbon of the carboxylic acid there, that would be that carbon there of the primary alcohol. And there is a mechanism to this, but I don't think Wei went over it, so I won't show you it just to not overwhelm you. But let me just make sure if she went over that mechanism or not. Of reducing a carboxylic acid down. Yeah, she didn't go over that mechanism. So I wouldn't worry about that, right? Or if you're interested, I can show you the mechanism of this.
Okay.
Yeah, so let me show you the mechanism. When you see lithium aluminum hydride, we know that the lithium has a full positive charge, aluminum has a negative charge because it is directly attached to the lithium. So this aluminum here will be negatively charged, with these hydrogens being the hydride ions, right? And those hydrogen ions here, think of them as a strong nucleophile and base. But if it has a chance to, it will act as a base over the nucleophile, because acid-base reactions in ochem are the fastest, one of the fastest reactions. So if it has a chance to act as a base, it's going to act as a base over the nucleophile, which in this case it does, because we have an acidic hydrogen here, which is the hydrogen of the carboxylic acid. Right. So instead of attacking this carbonyl carbon right here, we're going to deprotonate the carboxylic acid, grab that hydrogen, and give that oxygen a negative charge. Right. Does that first step make sense?
You said that the hydrogen is acidic, so we want to deprotonate it from the bond that hydrogen is attached to aluminum.
Yes, we want to attack this acidic hydrogen here because this hydrogen right here in purple is the base, the hydride ion, the base and nucleophile. And it has the option of attacking the electrophile carbon here, or the option of grabbing this acidic hydrogen. And we said earlier that it would prefer to act as a base, grabbing the hydrogen, acidic hydrogen, over attacking the electrophile carbon because acid-base reactions are one of the fastest reactions in ochem.
Oh, okay.
So that's why this nucleophilic or basic hydrogen here is going to grab that acidic hydrogen instead of attacking the carbon right there.
Okay.
And that's going to give this negative charge here, which is going to be our intermediate, but we have excess amount of LiArLH4. So I'm going to bring in another equivalent of it to attack that carbonyl, pop the double bond onto the oxygen, and give us this intermediate here. Right. Where I'm going to draw out the hydrogen right here that attacked it, which is going to be this hydrogen right here in yellow. We have O minus here, another O minus here. Right. But then let me go backwards here in the mechanism, because I'm going to do this at the same time, concerted step. Right. Where, you know how we used this hydrogen here, the one in yellow, to attack that carbon right here?
Yeah.
At the same time, this aluminum here is going to lose 2 electrons. So just imagine the 2 hydrogens, the 2 electrons there with the hydrogen is gone. Right. That means that the aluminum has 3 bonds and an empty p orbital, right? Because it's missing 2 electrons right now.
Okay.
Right. So because it's missing 2 electrons, this O minus here is going to attack that aluminum at the same time, right? Because as this aluminum here is losing this bond with hydrogen, it's going to gain a bond to that O minus right there. Because as the O minus senses that there is an empty p orbital here waiting to be attacked, the O minus is going to attack it right away at the same time as the hydrogen leaves. Right. So that's going to give us this intermediate here, where this is the new bond that we formed between this O minus and aluminum right there. Right. So that's why the oxygen is now neutral. And this aluminum still has 4 bonds, right? 1 to oxygen and 3 to hydrogens. That's why it is negatively charged still.
Okay.
Right. So now think of this as a good leaving group, like bromine, chlorine, or iodine. The O minus here is going to go back down to reform the carbonyl, carbon double bond oxygen, and kick off that good leaving group and result in our aldehyde right here. Right. And we won't stop at the aldehyde final product, because this aldehyde here is susceptible to be attacked by another LiAlH4. We have an excess amount of that. So we're just going to reduce that aldehyde to reach our primary alcohol. And we did that mechanism at the beginning of this session here. Right. What the H minus of the reducing agent will attack that carbon. And we bring in the second step, acid workup, to protonate the O minus to become the neutral OH, giving us our final primary alcohol there. Right.
So when do we know when to stop, like, continuously adding our unlimited amounts of?
Yeah, so we know when to stop when, in this case, where there's no more carbonyls, no more carbon double bond oxygens. Right, because whenever we reduce these here, we always stop at the alcohol, primary alcohol, secondary alcohol, or primary alcohol here. Right.
Okay.
Yeah. Okay. Yeah. So to summarize everything in the table here, if you have an aldehyde and you want to go back into primary alcohol, you could either use NaBH4 or LiAlH4 first step, second step acid workup. If you want to reduce a carboxylic acid down to a primary alcohol, you would use LiAlH4 second step acid workup. If you tried using NaBH4 on a carboxylic acid, you would get no reaction. No reaction. So the way you might put that kind of problem there, because I've seen this before, where they put a carboxylic acid as the reactant and they try to react it with NaBH4, a weak reducing agent. That would give us no reaction. If you want to reduce a ketone into a secondary alcohol, you could use NaBH4 or LiAlH4, second step acid workup. Like that.
Okay.
Yeah. So that yeah.
Yeah. Oh, I was wondering if we could see like the last problem that we worked on real quick.
Yeah. This last problem here, I wouldn't worry about the mechanism too much since she didn't show it, but just in case you need to know it, this is the mechanism here. But the most important thing here is that we had to use LiAlH4 to reduce a carboxylic acid down into a primary alcohol. Right? And we know we reduced it because we gained the bonds to hydrogen and we lost bond to oxygen.
Right.
Mm-hmm.
That was reduction?
Yeah, that was reduction of alcohols. So all of this here, this whole table here is including all of the oxidation and reduction reactions for alcohols.
Okay. And the reduction is what you wrote in red?
Yes, all the ones in red are reduction.
Okay.
Yes.
And you said that we keep reacting until we don't have any more double bond to oxygen and we're left with like a alcohol?
Yes, for reduction.
Oh, for reduction, yeah.
Right. And then you might also see this where you might start with an aldehyde, and if you want to oxidize that further into the carboxylic acid, you would have to use the strong oxidizing agent Jones.
Okay.
Right. If you use PCC, it would not do anything. It would not go down to carboxylic acid because PCC is a weak oxidizing agent.
You said it wouldn't because why?
Yeah, sorry.
Oh, can you hear me?
Hello.
Yeah, I can hear you. Can you hear me?
Oh, yeah, I can hear you. I heard you at you said I could what? Sorry, my internet cut off.
You said that could happen. That won't react. Why? Or I think with PCC.
Yeah, because PCC is a weak oxidizing agent, so it cannot oxidize all the way to the carboxylic acid. We need a strong oxidizing agent to get to that oxidized state. Right, carboxylic acid is to oxidize for PCC.
Oh, right. Okay.
Right.
So can we use Jones?
Yeah, we can use Jones. Right.
Okay.
So if you have an aldehyde and you use Jones, that's going to convert the aldehyde into the carboxylic acid.
Okay.
Right.
Okay, that makes sense. Thank you so much.
Yeah. No problem, Elysia. Okay. Hey, Christina. Hey, Zinyan. 118C. Let's see. So, you said quinoline and isoquinoline, the benzyl pyridines, chichibabin reaction from chapter 25. Alkaloids.
I kind of just put what we covered today. But we can start anywhere, like among, yeah.
Yeah. Okay, let me get his notes so I can see what he wants to go over. So then I make sure I don't like show you the wrong reactions for the wrong class. Let me try to find his lecture notes here. Lecture notes. Chapter 25. This one. Okay.
I was kind of like at the end where he was talking about doing like an antimerically pure like amino acids, like because he was kind of talking about how like S is the most common, and like when we're synthesizing drugs, we only want the S configuration or something like that.
Right, because most amino acids are in the S configuration, so we want it to be in that because that's the amino acid that is used in like biological systems. But in the end of chapter 26, lecture part 2. Was that today?
Yeah, he finished chapter 25, 1 and 2, and then he started chapter 26, and he got to like, I don't know if you have the slides. He got to like slide 8 if you have those ones.
I have the part 1 ones. I have the part 1 amino acids, peptides, proteins.
For 25 or 26?
Oh, 26. Oh, are you talking about chapter 25, part 2? Part 2?
So yeah, that was kind of the end of chapter 25, and then yeah, he went into chapter 26. So that's the part that and part 1. So you're
Part
yeah.
1. Yes, part 1. Amino acids. Okay. Oh, slide 8. It's 8, 8, 8, 8. Okay, okay. Let me see. Oh, I see, I see. Synthesis of enantiomerically pure amino acids. Yes.
Mhm.
Resolution of diastereomer salts of amino acids. The amine group is first protected by to an amide. The amide is treated with optically active amines such as inexpensive alkaloid. The two, there's some sort of disadvantage, can suffer from yields prep of enantiomer at C2 very zeokine above hydrogenated using pure rhodium catalyst using all R ligand shown to give the S product exclusively, which is hydrolyzed S-phenylalanine. Conversely, the same hydrogenation is the same in the presence of the all S ligand furnishes the R enantiomer of the product and hence provides a synthesis of R-phenylalanine. This phenomenon is called where the catalyst directs the reaction towards specific chiral outcome.
And then it said like inexpensive alkaloid brucine, and I've never heard of brucine before either.
Brucine. Yeah, so the second step here is talking about how if we use an enzyme or ligand or substrate that is that has a chiral center and is chiral, that would lead to a product that is going to selectively select for one enantiomer over the other, right? So it depends on the enzyme and substrate you use and the type of reaction that you use. So in this case, you just have to know that rhodium catalyst bearing the all R ligand will lead to the S product, to the S amine. So it's more of a conceptual biochemistry thing. Like the enzyme or substrate has an effect on the product's stereochemistry, basically, right? Because if we like do an SN1 reaction, let's say for example, with this haloalkane with water, we know that the first step is to kick out the leaving group and form this carbocation. And then whenever we have a carbocation, we always look up for a carbocation rearrangement step, like a hydrogen shift or methyl shift, which in this case, we do have a hydrogen shift available here, which is going to form a carbocation at the more stable tertiary position, right there, right? And if we're doing SN1, the nucleophile water would attack that carbocation, which is sp2 flat and planar, right? So let me just make this a chiral center by making this a different group. If that's the case, then I'm just gonna skip the deproteination step, but deprotonate the H2O plus to create the OH, deprotonate. We could either get this product or this product is right here, right? Because the water could have attacked on the top side, giving us the wedge product, or it could have attacked on the bottom side, giving us the dash product. Right? And this is what we call a racemic mixture, which is a 1-to-1 ratio of enantiomers. Right? And we cannot select for this. It will spontaneously form both products equally, 50-50. 50%, 50%. But if we put some kind of chiral enzyme in here or chiral ligand in here, and depend on what the ligand is, it could selectively select for one enantiomer over the other. Right? And that's what number 2 is talking about. If we use rhodium catalyst bearing the all R ligand, that would lead to the S product. if it bears the alt S ligand, then that would lead to the R product, amino acid. Right. The first reaction that they were talking about, the resolution of the diastemic salts of amino acids, that's more of like the SN1 type reaction where you get a mix of enantiomers, basically. Right. Where let's say we have this carboxylate. Or amino acid, I mean, let's say this amino acid with this R group, valine. Valine. And what did they do here? Okay, so I'm just gonna write out this reaction mechanism and explain to you this step here. They added formic acid, HCOOH, which looks like this, and that led to this product here. This carboxylic acid. So we protonated the carboxylate into the carboxylic acid. The amino group, the amino group got acylated. So think of chapter 20 reaction or 19 reaction, where we form an amide from this carboxylic acid here. So this carboxylic acid here did two things. It protonated the carboxylate into the neutral carboxylic acid, and it also reacted with this amine group to create the amide. Right there.
This happens at the same time, or does the carboxylic acid get protonated first and then it attaches to the amide group?
Yeah. I would say the carboxylate gets protonated first because in ochem, acid-base reactions are one of the fastest reactions we have. Right? This reaction here with the amine and carboxylic acid reacting together is a nucleophilic acyl substitution. So it's a nucleophile electrophile reaction, which is slower than acid-base reactions.
Okay.
Right. So now once we have that, water got kicked off, which is the leaving group of that carboxylic acid right there when we form this amide. Right.
We're using excess formic acid?
Okay. Excess, right? Excess amount of formic acid. The first equivalent would protonate the carboxylate into carboxylic acid, and then the second equivalent would react with the amine to create the amide, right there. Right. Okay. And this right here, what we drew earlier is R S valine, right? Because I didn't give stereochemistry, so it could be the R or S valine amino acid. The product we reproduced is an R S N to represent the nitrogen of the amino group, amide group, formal valine, right? And this formal group right here, is talking about that formal group right there, right? So when we react this with brucine, which is abbreviated as B asterisk, B star, methanol in 0 degrees Celsius, we're going to get two different products here. And I'm just going to draw it out and explain to you why we get two different products here. So this is going to be Fischer projection, where we have the carboxylate, O minus, where this brucine is ionically bonded to it. And this is the R group. That's the alpha carbon. This is the hydrogen. This is the amide group with the
what's an alkaloid again? I know it's brucine, but does it have like
an alkaloid? Oh, it's like talk about Gen Chem. I think it's one of those alkaloid metals. There's alkaline, alkaloid. I think it's in group 2A. I'm not too sure.
Okay.
Too sure, yeah. I think Wiley knows. What he's a Gen Chem god. Yeah. So maybe Wiley could explain what alkaloid is. Mhm. Right. And the other one we could have is when the amide is on the other side.
And this is the R and S configurations, basically.
Yes.
Okay.
RNS configuration thing. We get like 2 different enantiomers here.
And enantiomer is the same thing as racemic.
Enantiomers is the same thing as racemic if it's a 1-to-1 ratio of enantiomers.
Okay.
Right. If it's not a 1-to-1 ratio of enantiomers, like let's say 64, 36, a ratio of enantiomers, then we cannot call that a racemic mixture.
Okay.
Right. But what they're saying here is that they are diastereomers. And do you remember the definition of a diastereomer?
It's where at one center they're flipped.
That's a specific type of diastereomer, which is an epimer. When only one chiral center flips and everything else stays the same, that is a diastereomer, an epimer. But the more like broad umbrella term is that some chiral centers change and some chiral centers stay the same. Because let's say a molecule has 4 chiral centers, and then you have 2 different molecules where 2 of the chiral centers are the same, but the other 2 are different. Those are still diastereomers of each other.
Okay.
Right. Diastereomer separate by fractional crystallization. Yeah, this is some other reaction that I have not learned before. This is covering something else, but I'm trying to figure this out right now with you. It's the diastereomers, because let's see, we do have a chiral center here, but I'm trying to find out where the other chiral center is. This is not the chiral center because it has 2 methyl groups. What is the other chiral center here? What? CH chiral center. How are these diastereomers? These looks like enantiomers to me. The 2 diastereomers formed are separated by fractional crystallization. Diastereomers, brucine. Okay, I think I know why, because it might be coming from the brucine here. The other chiral center might be this B, but I don't know what the structure of what brucine is. It might be some like big molecule with chiral centers in them.
Probably like what the that RH catalyst looks like, how it's like that super big thingy.
Yeah, I see it. Yeah,
Okay.
it's like a very big molecule with a lot of chiral centers. It's probably something like that. Right.
Yeah, because I think that the RH also has an asterisk, so I'm pretty sure that the brucine's probably something similar.
Yeah, because the asterisk represents a chiral center in
Okay.
ochem. So when you see asterisk, then that usually means a chiral center, chiral carbon sterol center. Same thing, right? Where that brucine chiral center there will stay the same, right, compared to these 2 molecules. But these red chiral centers here, the alpha carbon of the amino acids, chiral center flipped, right? So when some chiral centers stay the same, some chiral centers flip, we call these diastereomers of each other. Diastereomers. And diastereomers are separable, purifiable through their differences in physical properties or chemical properties. And there's different methods to do that, but the method that they use in this reaction is that they separated it by a lab technique called fractional crystallization. Separate by fractional crystallization. So if I were to guess what this test does, is that it would separate the ionic bonds like somehow, because I see the word crystal. So
So when they say like AR.
Yeah, so the next thing here is that once we get this intermediate right here,
Mhm.
we just want to get rid of that. That's our pure amino acid, because a pure amino acid, it's just gonna have a carboxyl group, an amino group, an R group, and an alpha hydrogen, right?
Mhm.
So to deprotect that and get rid of the brucine, we use base and water at 0 degrees Celsius. Base,
Okay, okay.
water at 0 degrees Celsius. And that's just gonna get rid of the brucine chiral center. And it will also do another thing as well. It will get rid of the brucine chiral center and convert the amide back into the amino group. That one and this one here. So I'm gonna recap everything that I draw this final product here, right? Where this is gonna be S valine. This is gonna be R valine, which are enantiomers of each other, but we could separate them by fractional crystallization. And I'm getting kind of confused with the percentage here because they're saying this is 70%, this is 70%. Maybe they are in their own separate flasks. So that's why they have different percentages. After we separate them by, right? I'm kind of curious if this is actually S. Let's see here. See, this is 1, this is 2, this is 3. So this looks R. Because the lowest priority group here, the hydrogen, is on a wedge. So we just flip whatever it looks like to an R, to the other thing, which is an S, right? Which would make this 1, 2, 3, going this way. Looks S, but is R, right? So yeah, this checks out. This is R valent, this is S valent, and then we separated them by fractional utilization. Okay, so to recap everything, we started off with a mixture of R and S valine. You could say a racemic mixture, where there's a 1-to-1 ratio between R and S valine. And let's say that in lab, we wanted to purify this valine, only receive and isolate the S valine for us to work in like biological conditions. To do that, we use formic acid in excess amount, which is going to do two stories. It's going to protonate the carboxylate into the carboxylic acid and do a nucleophilic acyl substitution reaction to create an amide. It's going to be the reaction from the amine here and formic acid forming this amide here, chapter 19, right? Nucleophilic aromatic substitution. Once we get that, we use a chiral ligand called brucine, which is going to create two different diastereomers here. Like the point of adding brucine here, the biggest takeaway here is that brucine would create diastereomers. And diastereomers are very important in lab because they are separable. Right? In that are hard because they have like the same like conditions, basically. It's the same chemical or physical properties. I can't remember which one, but they're hard to separate. They have the same properties, whereas different properties. So that's the reason why we use brucine to create diastereomers here, which would like flip the chiral center on the alpha carbon, which is good. Like this would be the S, this would be the R, but we can't stop here, right? This is not a pure amino acid. So we don't want that amide there. We want that to deprotect it. Right. So the separation step is actually happening here. We're separating, right, we're just gonna separate them into two different flasks like this, right, like that. And then at those two different flasks, to get base water in 0 degrees Celsius of the brucine, chiral ligand, and do hydrolysis of amide back to the amine leaving group, and there's gonna be carboxylic acid flowing somewhere, right? Once we do hydrolysis of the amide, right? So this is talking about more of a lab thing. Like this is more of a lab reaction and technique, conceptual thing.
So, because brucine and brucine and rhodium are like really bulky, and we use the R base. That's why it will give the S configuration per se.
Yes, you think of it like that because the brucine is very bulky. That would tend to lead to the S configuration because that would like lead to less steric hindrance if it if it actually is avoiding steric hindrance in the S configuration, which is why it is going to prefer that S configuration.
Okay, okay.
Because once you add that bulky R group or ligand there, with the chiral centers, that could like because the product wants to avoid steric hindrance. They want to have the most together, like opposite charges attract as well, and that would like cause different products to form selectively.
Okay, that makes a lot of sense. Thank you so much.
Problem. Yeah, like you see here the brucine avoids steric hindrance,
Do you
and
think
they will have
that
different properties separating them.
Mhm.
And this one class S valine, this other class we have valine. Interested in this one here.
Do you think that brucine and rho RH are interchangeable?
My home Wi-Fi for some reason. Oh, hello.
Yeah. Do you think that brucine and RH are like interchangeable?
Brucine and RH. If you see R asterisk H, then that is gonna talk about like a generic ligand that is chiral. But if you see B asterisk, then that is specifically. Hello, can you guys hear me?
I can hear you.
Okay, yeah. My internet got cut off on my computer, so I'm gonna talk on my iPad right now. Can you still see my iPad screen?
Yeah.
Yeah. So the question was, what was the question again?
Is brucine and RH asterisk interchangeable?
Yeah. So the RH asterisk is gonna talk about a chiral ligand, and that's umbrella term and generic term because there's a lot of chiral ligands. When you see B asterisk, then that's talking about the brucine chiral ligand specifically, right? You can see other RHs that might not be brucine. The R might be something else. Right, but B would represent brucine
Recording
specifically.
in progress.
Yeah. Yeah. Any other questions on this? Oh shoot. Oh, okay. Yes. Okay. Yes. So, Elysia, let me give you some practice songs on reduction of alcohols, and we'll end office hours there. Yeah, no problem, Christina. Let's see. Let's see here. Give you 4. This is the first one. This is the second one. This is the third one. And then the last one I want you to try is this here. Okay. Yeah, try these 4 reduction reactions. But you're comfortable with the oxidation reactions, right?
Which reactions again?
Oxidation, like PCC Jones.
Oh yeah, I think
Yeah.
I'm pretty comfortable with those.
That's good. That's good. Now let's go the reverse direction, reduction, with these practice problems.
Okay, yeah.
Okay. Yeah. So office hours are
Thank
ending here
you.
tonight. Yeah, no problem, Elysia. Do you guys have any like tests tomorrow? No tests tomorrow, right? Like you guys are just chilling this quarter, this week.
Yeah, I just finished a quiz today, so like if I really wanted to, I can go back home.
Yeah.
But I know everyone else is gonna go home tomorrow, so I'm probably just I'm gonna avoid traffic and go Thursday.
Thursday. Yeah.
Yeah.
That's good. Yeah. Right. Okay. Yeah. So thank you guys for coming. I will see you guys tomorrow.
Oh, wait, I have a question.
Yeah.
So I know it's still gonna be Thanksgiving, so like is there any changes towards the schedule? I mean, I probably should check, but
Right. I'm not too sure yet because I have a family Thanksgiving party on Saturday, so I don't know if I have anything planned for Thursday yet. But right now, it's still going to be still as planned. But if there's any changes, I'll update on the calendar.
okay, thank you.
Yeah, no problem.
See ya.
See ya, Alicia.
Have a good night.
Good night. Good night.
I have a really, really quick question.
Yes.
I was just on the it was just C. I wasn't sure like if you hydrolyze this, do you get like a squiggle line for both of the OHs?
No, only the one with the anomeric carbon.
Okay, and that would be like a OH or like a CH2 OH?
That would be an OH.
Okay.
Right, with the same bond. So you know how that bond is going equatorial down?
Oh, that would be okay.
That will stay as an equatorial down OH. And then the one with the anomeric carbon with a squiggly line OH.
Okay.
Right.
Okay. Yeah, that was my only question.
Yeah. Yeah.
Yeah, thank you so
Homework.
much.
Yeah.
Well, have a happy Thanksgiving, Brian.
Yeah, you too, Zunyan.
Bye.
Good night. Bye.